To demonstrate how to use a hypothetical process path and how they work, we're going to go through example 8.4-2 from the textbook. And so in this example problem, what we're dealing with is 100 moles per hour of liquid hexane coming into a process at 25C and 7 bar, and it's going to be vaporized and heated to 300 degrees Celsius at a constant pressure. And so for this process, what we're going to do is we're going to estimate the rate at which heat must be supplied. And even though this example tells us to ignore the effective pressure, let's not do that, because I actually want to show you how to account for changes in pressure for this system. Okay? All right, and so based on this modified problem statement, what I want you to do now is pause the video and draw the process flow diagram, and also identify a basis, and also start drawing your enthalpy table as well. Based on the information in this problem statement, we could draw a process flow diagram that looks like this, where a basis for the process is that 100 moles per hour. All right? And so the inlet to our process has a feed of 100 moles per hour of that N-hexane at a temperature of 25 degrees C and a pressure at 7 bar. All right? The outlet is also at 7 bar because the process is being heated at a constant pressure, and it's being heated to a temperature of 300 degrees C. Okay? Now, down here I set up the enthalpy table, and you could see at this point I've already kind of thought ahead and set up the fact that my reference state for the hexane is going to be in the liquid phase, and it's going to correspond to the inlet conditions, right? Specifically, the inlet is a liquid at 25C and at 7 bar. And we're going to fill in the rest of this table as we go through the problem. Now, as far as things we don't know, we're interested ultimately to figure out the amount of heat that's needed in order to vaporize the N-hexane. And technically, we don't know the outlet flow rate of the N-hexane as well. Okay, so at this point, we've identified the unknowns, and so what we need to do now is figure out if we have enough information to solve for those unknowns. So we'll do a degree of freedom analysis. And so our number of unknowns is 2, and our unknowns include N2 and also the heat flow rate. The number of chemical species we have is just 1. We just have that hexane. Even though it's going to be in 2 phases, it's still just the same chemical species. And as far as other equations we could use, we could always use our energy balance. And so now our degrees of freedom is going to be equal to 2 minus 1 minus 1, which is 0. Alright? So, now that we've shown we have enough information to solve the problem, let's go to our material balance. Right? We're dealing with an open system that's at steady state. There's no reaction going on. Even though it's a phase change, it's not a reaction. All right? So G minus C, that's going to correspond to 0. And so what we're left with is inputs equal to output, or in other words, N1 is equal to N2, which is at 100 moles per hour. All right, so that's a very simple material balance. Let's now go to the energy balance. For the open system, our energy balance is delta H plus delta EK plus delta EP is equal to Q plus WS. All right, we're not really going to consider any changes in kinetic or potential energy, and there's nothing spinning, or there's no pumps in the system, so we don't have to worry about shaft work. So what we're left with is that the change in enthalpy is equal to just our heat flow rate. Right? And so if we want to figure out our heat flow rate, we need to calculate that delta H. And it's only going to be useful to us if we expand out delta H into its specific enthalpy form. And so we're going to start with the final, which is N2 H2 hat minus the initial, N1 H1 hat. Okay? Now, because I set my reference state to be the inlet conditions, that means that at our inlet, even though our flow rate is 100 moles per hour, our enthalpy, we're going to set that to 0. Okay? So I'm going to cross out this because it's at the reference state. And so what we're left with is our delta H is just N2 times H2 hat. Okay? Alright, and so we already know what N2 is. And so in order to solve for the heat, we just need to figure out what H2 hat is. Right? Okay, and so for that, basically what we're dealing with is just, in this process, a liquid that goes to a vapor. Okay? Alright, so we could go to table B1, and let's do that now, and we could look up the values for N-hexane. Alright, so we're going to be looking at 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. The fourth and third column, or sixth and fifth columns from the right. So pay attention here. Look at TB and HV. Right, and so we're going to scroll down all the way until we see N-hexane. Alright, and so I'm going to scroll that to the top. Alright, and so the N-hexane values, we see that we could find its delta HV. Right, it's 28.85 kilojoules per mole. Alright, but what we have to remember is that this HV is for hexane at 1 atmosphere. Right? But in our process, both our inlet and our outlet pressures, P1 and P2, are at 7 bar. Right? And so at this 1 atmosphere, we see that the boiling point temperature for N-hexane is 68.74. Okay? But what is it if we're at 7 bar? Right? Right? If we're changing pressure, then we're changing the boiling point temperature. Okay? And so, just to write out what we've seen so far from table B1, we see that HV hexane is equal to 28.85 at a pressure of 1 atm and a boiling point temperature of 69 degrees Celsius, roughly. Okay, but for us, the issue is equal to 7 bar, so about 7 times the atmospheric pressure. Okay? Alright, and so the question we have is, what is TB at 7 bar? Okay? So, how can we figure that out? You know, to be quantitative about it, what we could potentially do is we could go to Antoine's equation. Right? Because Antoine's equation relates the boiling point temperature to pressure. So P equals P, the vapor pressure of P hexane at 10 to the A hexane, B hexane, TB plus C hexane. Okay? Right? And if we solved for TB from Antoine's equation, we would get a TB value of 146 Celsius. Right? So that's much higher than the 69 degrees Celsius that we find in the back of the book. Alright? And so, this could be an issue. Right? The delta HV that we have access to in table B1 may not be the same at the at the boiling point temperature of hexane when it's under a pressure of 7 bar. Okay? And so what I want to ask is this going to be a problem for us? Right? And so I want you to pause the video here, and I want you to think on how we could solve this problem. And so at P1 equals P2 at 7 equals 7 bar, you know, the actual boiling point temperature is going to be at a much higher temperature than whatever the tabulated value is in the back of the book. Okay? But it turns out this is not actually a problem for us. Right? And the reason for that is because, in the end, we're just going to develop a hypothetical process path that allows for us to both phase change the hexane from a liquid to a vapor, and also ends with it at 300 degrees Celsius and at 7 bar. Okay, so just need a path that includes both delta HV at TB equals 69 degrees Celsius and 1 atm, and ends at T equal 300 degrees C and 7 bar, or P equals 7 bar. Okay. Okay? And so here's what we're going to do. We're going to follow the instructions from that previous video, right? And so I'm going to kind of visualize it out by writing it out. And so what we're going to do is we're going to say we start with hexane at its inlet conditions, right? And so its inlet conditions were the liquid at 25 degrees C and at 7 bar. Specifically, we're starting with hexane at the reference state, right? Because that's where we want to do all our math from, okay? Because that's going to be the 0 state. All right, so we start with hexane at this reference state conditions, and then what we do in step A is we're going to reduce its pressure. So we're going to keep the same phase, keep the same temperature, but we're just going to lower the pressure down to 1 atm. Okay? Then in our next step, what we're going to do is we're going to keep it as a liquid, keep it at the same pressure, but now we're going to heat it up to 69 degrees C. So it's atmospheric, it's normal boiling point. So this is step B. Okay? In step C, what we'll do is, since we're at the boiling conditions for hexane at 1 atmosphere, we're going to undergo a phase change. So we're going to change it from a liquid to a vapor. Keep the same temperature, keep the same pressure. Right? Then once we're a vapor, in step D, we're then going to raise the temperature of the vapor and keep the same pressure. And then finally, in our last step, step E, we're going to stay as a vapor, stay at 300 degrees C, and then just raise the pressure. Okay? Alright, and so that's what I mean by developing a hypothetical process path. So rather than just going directly from the inlet conditions to the outlet conditions, in order to account for both the liquid to vapor transition and also, the heating as well, we kind of think of additional steps, right? And the reason for that, just to emphasize, the reason we develop these hypothetical process paths is because for enthalpy, all that matters is the difference between the final state and the initial state. Okay? So that's why we could use these hypothetical process paths in order to calculate delta H, even if the phase changes occur at conditions that are not the same as the conditions listed in the back of the book. In any case, to calculate our H2 specific, okay, what we're going to do is we're going to take the enthalpy change associated. Let me go back. Chapter 8. What we're going to do is we're going to basically calculate the enthalpy change that's associated with each of these steps. Okay, so delta HA plus delta HB hat plus delta HC plus delta HD plus delta HE. Okay? Alright, and so let's figure out how to calculate each of them. Alright, so for delta HA, what we're doing is we're taking a liquid and we're just reducing its pressure from 7 bar to 1 atm. Okay? And so when we deal with incompressible fluids and we keep them at a constant temperature but we change their pressure, their enthalpy is just going to be equal to the specific volume times that pressure change, right? So that pressure change, final mass initial, we have 1 atm minus 7 bar. I'll skip doing the calculations for to get all the units consistent. But in any case, in the end, if you go through the calculation properly, you get a delta H change of negative 0.0782 kilojoules per mole. For delta HB, all we're doing is just heating that liquid at 1 atmosphere from 25 to 69 degrees C. And so to account for this enthalpy change, we just go to the back of the book and we look up the heat capacity constants for hexane as a liquid. And if you do that, I'll leave it up to you to work out the steps, but if you do that, you get a final answer of 9.44 kilojoules per mole. For step C, this is where we actually change from the liquid to the vapor. And so since we're at the conditions that are coincident with the tabulated conditions in table B1, we could just take that HV value, right? And so that's going to be 28.85 kilojoules per mole. For step D, what we're doing here is, now that we've changed to the vapor, we're going to heat it from 69 degrees C up to the final 300 degrees C. Alright, so this is hexane vapor. I'll put that for emphasis. If you look up the heat capacity constants from the back of the book and do the integral, you should get a value of 47.1 kilojoules per mole. Alright, and then the final step is we're taking that vapor and we're just changing the pressure. Now if you remember from the earlier videos, if you're dealing with an ideal gas or even a non-ideal gas, we could basically assume that changes in pressure will not affect the enthalpy. Alright, so for a gas, if you're only changing pressure and you're keeping the phase and the temperature constant, the pressure will not influence the enthalpy. Okay? And so these are our values for each of the different steps in calculating H2. And so if you take all these things and then add them up, what you get is that H2 is equal to 85.5 kilojoules per mole. And vicariously, your Q dot is just going to be 100 moles per hour times 85.5 kilojoules per mole, right? And then we can convert the kilojoules per hour into kilowatts by just changing hours to seconds, and we know 1 kilowatt is equal to a kilojoule per second. Okay, and so what we get at the end is it takes 2.38 kilowatts of heat in order to vaporize that hexane. Okay, and just for completion's sake, I'm also going to fill out our enthalpy table. All right, and so By using or utilizing a hypothetical process path, we avoided the complexity of basically vaporizing our hexane at conditions that are not the same as the conditions that are listed in Table B1.